Something impossible is happening in our universe right now, not in some distant galaxy or theoretical equation, but everywhere, all around us at this very moment. There are things moving faster than physics says anything should move, faster than Einstein claimed was possible, faster than the ultimate cosmic speed limit that supposedly holds our entire reality together. Scientists have measured it, satellites have detected it, and it's shattering everything we thought we knew about the fundamental laws of nature. Today we're confronting a question that physicists whisper about but rarely discuss publicly. What if the speed of light isn't the limit we've been told it is? If you're fascinated by the universe's deepest mysteries and want to explore more cosmic paradoxes, make sure to subscribe to this channel and give a thumbs up. And here's a question for you. If you discovered a way to travel faster than light, but using it meant you could never return to your own home, would you take that journey? Let me know why in the comments down below. I will pin the most creative answer. Now let's begin. Let's start with why this question matters so profoundly. The speed of light isn't just a number, it's the universe's fundamental constant that governs causality itself. It determines how quickly cause can create effect, how fast information can travel, and ultimately whether the past can influence the future or vice versa. Einstein showed us in 1905 that this speed limit isn't arbitrary, it's woven into the geometry of space-time. But here's where things get weird. We've discovered phenomena that seem to violate this sacred limit, and understanding them will transform how you see reality. First, let's establish what we mean by faster than light. When physicists say nothing can exceed light speed, they specifically mean nothing with mass can accelerate through space faster than light travels in a vacuum. This distinction is crucial because, as we'll see, there are loopholes, ways the universe permits apparent faster-than-light phenomena without actually breaking Einstein's rules. It's like finding legal ways to exceed the speed limit without technically speeding. The story begins with quantum entanglement, what Einstein famously called spooky action at a distance. When two particles become entangled, measuring one instantly affects the other regardless of the distance between them. In 2015, scientists at the National Institute of Standards and Technology demonstrated this effect with particles separated by distances that light would take measurable time to traverse. The correlation happens instantaneously, faster than light could carry a signal between them. But here's the catch that saves Einstein's theory. No usable information actually travels between the entangled particles. You can't use entanglement to send a message faster than light. It's like having two magic coins that always land on opposite sides, heads and tails, no matter how far apart they are. The correlation is real and instantaneous, but you can't control which side your coin lands on, so you can't encode a message. The universe seems to have built-in safeguards against using quantum mechanics to violate causality. Now let's talk about something that definitely moves faster than light, the expansion of space itself. The universe is expanding and distant galaxies are receding from us at speeds that exceed light speed. The most distant galaxies we can observe are moving away at several times the speed of light. This isn't science fiction, it's observed fact confirmed by the Hubble Space Telescope and more recently by the James Webb Space Telescope. How is this possible? Because these galaxies aren't moving through space faster than light, space itself is expanding between us and them. Imagine drawing dots on a balloon and then inflating it. The dots aren't moving across the balloon's surface, but they're still getting farther apart. Similarly, galaxies can recede from each other faster than light because it's space itself that's stretching. The cosmic speed limit only applies to motion through space, not the expansion of space itself. This brings us to inflation theory, one of cosmology's most successful yet mind-boggling ideas. In the first fraction of a second after the Big Bang, specifically between 10 to the negative 36 and 10 to the negative 32 seconds, the universe underwent exponential expansion. During this brief period, regions of space flew apart at speeds vastly exceeding light speed. A region the size of a proton expanded to the size of a grapefruit in less time than light could travel across a proton. The evidence for inflation is written across the sky in the cosmic microwave background radiation. The Planck satellite and WMAP have mapped this ancient light with exquisite precision, showing patterns that only make sense if inflation occurred. Without this faster-than-light expansion, different regions of the universe couldn't have the same temperature. They would never have been in causal contact. Yet we observe remarkable uniformity, explained only by inflation's superluminal expansion. Phase velocities can also exceed light speed without violating physics. When light passes through certain materials, its phase velocity, the speed at which wave crests move, can exceed c, the speed of light in vacuum. This happens in materials with anomalous dispersion, where different frequencies travel at different speeds. Scientists have created materials where light pulses appear to exit before they enter, seeming to travel backward in time. But again, no information travels faster than light. The pulse that exits is reshaped from light that was already in the material. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, offers a theoretical way to travel faster than light without breaking physics. The concept involves warping space-time, contracting it in front of a spacecraft and expanding it behind. The ship never exceeds light speed locally, but the warping of space allows it to reach distant destinations faster than light could travel through normal space. It's like moving the universe around your ship rather than moving your ship through the universe. But before you start packing for Alpha Centauri, know that the Alcubierre drive faces seemingly insurmountable challenges. It requires exotic matter with negative energy density, something that might not exist in the quantities needed. Initial calculations suggested you'd need more negative energy than the mass energy of the entire observable universe. Recent refinements have reduced this to merely the mass energy of Jupiter, which is still impossibly large. Plus, the drive might create causality paradoxes, allowing travel into the past. Wormholes represent another potential faster-than-light shortcut that doesn't technically involve exceeding light speed. These hypothetical tunnels through space-time could connect distant regions of the universe, allowing near-instantaneous travel between them. You wouldn't move faster than light through the wormhole, you'd take a shortcut through a higher dimension, like tunneling through a mountain instead of climbing over it. The mathematics of general relativity permits wormholes, but keeping one open would require exotic matter, similar to what the Alcubierre drive needs. Speaking of our current limitations versus theoretical possibilities, if you're curious about humanity's actual space travel capabilities today, check out my video called "How Fast Can We Travel in Space Right Now?", where I explore the sobering reality of our current technology and what it means for our cosmic ambitions. The link is in the description below. Now back to breaking the universe's speed limit. Tachyons are hypothetical particles that always travel faster than light. In Einstein's equations, nothing prevents particles from existing above light speed. The barrier is only in crossing the speed of light. Tachyons would have imaginary mass and experience time backward from our perspective. As they lose energy, they speed up, approaching infinite velocity as their energy approaches zero. Despite decades of searching, no experiment has ever detected a tachyon. They remain mathematical curiosities that would revolutionize physics if discovered. The universe seems to play tricks with apparent faster-than-light motion. Quasars and jets from black holes sometimes appear to move across the sky at several times light speed. This superluminal motion fooled astronomers until they realized it's an illusion caused by geometry and light travel time. When a jet points almost directly at us while moving at speeds close to light, the light it emits at different points arrives compressed in time, creating the illusion of faster-than-light lateral motion. The universe is full of these perspective tricks. Quantum tunneling presents another case where particles seem to violate the speed limit. When particles encounter barriers they shouldn't be able to cross classically, quantum mechanics allows them to tunnel through instantaneously. In 2020, researchers at the University of Toronto measured photons that appeared to tunnel through barriers faster than light. But the devil is in the details. While the peak of the wave packet might arrive early, the information carried by the photon still respects the speed limit. Cherenkov radiation provides a beautiful example of particles exceeding light speed in a medium. When charged particles travel through water or other materials faster than light moves through that medium, they create a blue glow, the optical equivalent of a sonic boom. This is why nuclear reactors glow blue underwater. The particles aren't exceeding light's vacuum speed, just its reduced speed in that material. It's perfectly legal by physics rules and actually useful for detecting high-energy particles. The EPR paradox, named after Einstein, Podolsky, and Rosen, tried to prove quantum mechanics was incomplete by showing it allowed faster-than-light effects. Ironically, experiments have confirmed quantum mechanics is correct, and the spooky action is real. Bell's theorem and subsequent experiments by Alain Aspect and others proved that entangled particles really do correlate instantaneously. But the universe cleverly prevents this from violating causality. The correlations are random until measured, preventing faster-than-light communication. Let's dive into cosmic inflation more deeply. During inflation, the universe expanded by a factor of at least 10 to the 26. That's a 1 followed by 26 zeros. Regions separated by this expansion are now causally disconnected, beyond each other's cosmic horizons. Light from one will never reach the other, no matter how long we wait. This faster-than-light expansion created islands of causality in our universe, regions forever isolated from each other by the expansion of space itself. The Unruh effect predicts that accelerating observers see empty space filled with particles. At extreme accelerations approaching infinite values, these virtual particles might enable faster-than-light travel through quantum effects we don't yet understand. Some theories suggest the vacuum itself might be manipulated to create shortcuts through space-time, but these ideas remain highly speculative, awaiting a theory of quantum gravity to determine what's actually possible. Group velocity in certain materials can exceed light speed. Scientists have created setups where the peak of a light pulse exits a material before it enters, appearing to travel faster than light or even backward in time. But information still travels at or below light speed. It's like a line of dancers doing the wave. The wave pattern can move faster than any individual dancer, but no single dancer exceeds their maximum speed. The universe distinguishes between phase velocity and information velocity. Closed time-like curves in general relativity would allow faster-than-light travel by going backward in time. Some solutions to Einstein's equations, like the Gödel metric or rotating black holes, permit these curves. You could travel to a distant star instantly by going back in time to when it was closer, then forward to the present. But most physicists believe nature forbids these solutions through mechanisms we haven't discovered. Hawking's chronology protection conjecture suggests the universe conspires to prevent time travel paradoxes. Dark energy, the mysterious force accelerating cosmic expansion, might hold keys to faster-than-light travel. As the universe expands faster, more galaxies cross the cosmic horizon, becoming unreachable even at light speed. But perhaps understanding dark energy could reveal new physics, allowing us to manipulate space-time expansion. The discovery of dark energy in 1998 through supernova observations showed us the universe still holds fundamental surprises. Variable speed of light theories propose that the speed of light might have been different in the early universe. João Magejo and Andreas Albrecht suggested this could solve cosmological problems without inflation. If light speed can vary, perhaps it can be locally modified, but evidence strongly supports a constant light speed throughout cosmic history. The fine structure constant, which depends on light speed, shows no variation in light from distant quasars billions of years old. The quantum Zeno effect demonstrates how observation can freeze quantum systems, preventing change. Some theorists speculate that at extreme speeds approaching light, the universe's constant observation through particle interactions might create a similar freezing effect, forming an absolute barrier. It's as if the universe watches more carefully as you approach its speed limit, eventually stopping you cold. This might be nature's way of protecting causality from would-be violators. Let's examine what happens at the edge of physics, where our theories break down. At the Planck scale, distances of 10 to the negative 35 meters, quantum effects dominate gravity. Space and time might become discrete, pixelated like a computer screen. Some theories suggest faster-than-light travel might be possible by exploiting this quantum foam, jumping between pixels of space-time. But we're so far from probing these scales that it remains pure speculation. The holographic principle suggests our three-dimensional universe might be encoded on a two-dimensional surface, like a hologram. If true, what we perceive as faster-than-light travel in 3 dimensions might be perfectly legal motion in the underlying two-dimensional reality. Black hole physics hints at this. Information falling into a black hole seems to be preserved on its two-dimensional event horizon. Perhaps the universe's speed limit only applies to the holographic projection, not the fundamental reality. Cosmic strings, theoretical defects in space-time left over from the Big Bang, could enable faster-than-light travel. These infinitely thin but incredibly dense strings would warp space-time around them. Two cosmic strings moving past each other could create closed, time-like curves, allowing time travel and effectively faster-than-light journeys. Despite decades of searching, no cosmic string has been detected, though they remain possible in many theories beyond the standard model. The many-worlds interpretation of quantum mechanics offers a bizarre loophole. Every quantum event splits the universe into parallel branches. Perhaps what we call faster-than-light travel is really jumping between parallel universes where events happen differently. You don't travel faster than light, you shift to a universe where you're already at your destination. This sounds like science fiction, but some physicists take the possibility seriously. Within the mathematical framework of quantum mechanics, negative mass, if it exists, would have properties that defy intuition. Push it, and it accelerates towards you. Pair negative and positive mass, and they accelerate together indefinitely without any input energy. This runaway pair could theoretically reach any speed, including faster than light. But negative mass has never been observed and might violate fundamental principles like energy conservation. The universe seems to forbid such exotic matter. The Casimir effect proves that empty space has negative energy density between closely spaced plates. This gives hope for exotic matter needed for wormholes and warp drives. But the effect is tiny. The force between plates a micrometer apart is barely measurable. Scaling this up to useful levels for faster-than-light travel would require engineering beyond our wildest dreams. Still, it shows negative energy isn't purely theoretical. Brane theory suggests our universe might be a three-dimensional membrane floating in higher dimensional space. Other branes, parallel universes, might be millimeters away in these extra dimensions. Gravity can leak between branes, but other forces can't. Some theories propose using gravitational effects to communicate or even travel between branes faster than light could travel within our brain. It's a cosmic shortcut through dimensions we can't directly perceive. The Bootstrap paradox illustrates why faster-than-light travel threatens causality. Imagine receiving blueprints for a faster-than-light drive from the future, building it, then sending the blueprints back to your past self. Where did the information originally come from? Such paradoxes suggest the universe must prevent faster-than-light travel to maintain logical consistency. Every proposed method faces similar paradoxes that physics seems designed to prevent. Quantum field theory in curved spacetime predicts strange effects near the cosmological horizon. As the universe's expansion accelerates, the horizon shrinks and quantum effects might become dramatic. Some speculate this could create traversable wormholes or other faster-than-light phenomena. But we're talking about physics at the edge of the observable universe, billions of years in the future, hardly practical for space travel. The information paradox in black holes hints at deeper mysteries about space, time, and information. If information can't be destroyed, what happens to information falling into a black hole? Recent theories suggest it might be preserved through subtle quantum effects at the event horizon. Understanding this could reveal new physics about how information, and thus causality, works in extreme conditions. Perhaps faster-than-light travel is impossible because it would violate information conservation. Metamaterials with negative refractive indices can make light appear to move backward. Scientists have created cloaking devices and other exotic effects using these engineered materials. Some propose space-time metamaterials that could bend the path of matter itself, creating shortcuts through space. But manipulating space-time is vastly harder than manipulating electromagnetic waves. We can barely detect gravitational waves, let alone engineer them. The cosmic censorship hypothesis suggests nature hides any violations of causality behind event horizons. Naked singularities, where physics breaks down visibly, might permit faster-than-light effects, but the universe seems to always cloak them in black holes. It's as if nature has a modesty principle. Any place where its laws break down gets covered up. This might be why every proposed faster-than-light mechanism faces insurmountable obstacles. Analog gravity experiments use flowing fluids or Bose-Einstein condensates to simulate black holes and other gravitational phenomena. These systems can exhibit horizons where the flow exceeds the speed of sound waves, creating acoustic black holes. Studying these might reveal whether horizons and speed limits are fundamental or emergent properties. If emergent, perhaps the universe's speed limit could be circumvented under the right conditions. The vacuum of space isn't empty. It seethes with virtual particles popping into existence and annihilating in time shorter than the universe allows us to measure directly. This quantum foam might hold the key to faster-than-light travel. Some theories suggest that at high enough energies, we could surf these quantum fluctuations, using them as stepping stones through space-time. But the energies required approach the Planck scale, where our physics theories break down completely. Let's talk about the most successful theory in physics that might hint at faster-than-light possibilities: quantum field theory. It describes particles as excitations in underlying fields that permeate all of space. These fields can have non-local properties. Changes in one location can theoretically influence distant regions instantaneously through field configurations. But again, when we calculate what can actually be measured and communicated, the speed limit reasserts itself. The universe seems to have multiple backup systems preventing faster-than-light information transfer. The delayed choice quantum eraser experiment reveals just how weird quantum mechanics gets with time and causality. In this experiment, the decision to measure or not measure quantum information seems to retroactively determine what happened in the past. Some interpret this as information traveling backward in time, faster than light, in the most extreme way possible. But careful analysis shows no usable information actually travels to the past. The universe permits quantum weirdness but protects causality. Superluminal tunneling has been demonstrated with single photons and even atoms. When particles tunnel through barriers, they seem to cross the barrier instantly, regardless of its width. Mozart's Symphony. Number 40 has been transmitted through a barrier faster than light using frequency-modulated microwaves, but the information, the music, still arrived at light speed or slower. The leading edge of the wave packet arrived early, but it carried no information. Nature allows the illusion, but not the reality of faster-than-light communication. The GZK cutoff provides evidence that even the universe's highest energy particles respect the speed limit. Cosmic ray protons with extreme energies should interact with the cosmic microwave background, losing energy over long distances. We observe this cutoff, confirming that even particles with energies millions of times greater than our most powerful accelerators can't outrun light. If natural cosmic accelerators can't break the speed limit with such enormous energies, our chances seem slim. Loop quantum gravity, a competitor to string theory, suggests spacetime itself is quantized at the smallest scales. In this pixelated spacetime, the concept of continuous motion breaks down. Some theorists speculate this could allow discrete jumps through spacetime, quantum teleportation on a macroscopic scale. But the theory is incomplete, and even if correct, the effect would likely be limited to Planck-scale distances, far too small for practical travel. The black hole information paradox has led to the firewall controversy. Some solutions suggest that crossing a black hole's event horizon instantly incinerates you in a wall of high-energy particles. This firewall would exist because of subtle quantum effects needed to preserve information. If true, it shows how quantum mechanics can create absolute barriers in space-time. Perhaps similar quantum firewalls prevent any faster-than-light travel, burning up anything that tries to break the cosmic speed limit. Traversable wormholes require threading them with exotic matter to prevent collapse. Even if we could create negative energy, recent calculations show wormholes would be unstable to any perturbation. A single photon passing through could trigger catastrophic collapse. The universe seems to make wormholes theoretically possible, but practically impossible, tantalizing us with solutions that self-destruct upon use. The ER-EPR conjecture by Susskind and Maldacena suggests that quantum entanglement and wormholes are the same phenomenon described in different languages. Every entangled particle pair is connected by a microscopic wormhole. If true, this deep connection between quantum mechanics and gravity might reveal new physics. But these quantum wormholes can't be enlarged for travel. Trying to do so would break the entanglement, severing the connection. Time crystals, confirmed to exist in 2017, show that matter can exhibit periodic motion in time without energy input, breaking temporal symmetry. Some speculate that space crystals might exist, structures that break spatial symmetry in ways permitting faster-than-light effects. But time crystals don't violate thermodynamics or causality, and space crystals would likely face similar constraints. Novel phases of matter might bend the rules, but probably can't break them. The Fermi paradox gains new meaning in light of the speed limit. If faster-than-light travel is impossible, civilizations are forever isolated in their stellar neighborhoods. The Great Silence isn't mysterious, it's inevitable. Even if the galaxy teems with life, we might never meet our neighbors. The speed of light isn't just a physical barrier, it's a cosmic quarantine keeping civilizations apart. Perhaps this is for the best, preventing conflicts or contamination across the stars. Quantum computers might simulate faster-than-light travel without achieving it physically. By exploiting quantum superposition and entanglement, they could calculate outcomes of relativistic journeys without taking them. This computational faster-than-light travel might be the only kind possible, experiencing distant worlds through simulation rather than transportation. The universe might allow us to know about distant places instantly, but not travel to them. The anthropic principle suggests we observe a universe with an unbreakable speed limit because universes without such limits can't support observers. Faster-than-light travel might inevitably lead to paradoxes that prevent stable causality, making life impossible. We exist in a universe with a cosmic speed limit because universes without one self-destruct through temporal paradoxes. The speed of light isn't arbitrary, it's the minimum needed for a coherent, observable universe. The Novikov self-consistency principle offers a potential resolution to time travel paradoxes. It states that any events occurring through time travel were always part of history. You can't change the past because your time travel was already incorporated into it. This might mean faster-than-light travel is possible, but only in ways that preserve causality. The universe might allow apparent violations of the speed limit as long as they don't actually violate cause and effect. It's like cosmic accounting, where the books always balance. Recent observations of gravitational waves by LIGO and Virgo confirmed that gravity itself propagates at exactly the speed of light. When neutron stars collided in event GW1 70817, the gravitational waves and light arrived at Earth within 1.7 seconds of each other after traveling 130 million light-years. This near-simultaneous arrival proves that even space-time distortions respect the cosmic speed limit. If gravity can't exceed light speed, our hopes for warping space to achieve faster-than-light travel face fundamental constraints. The quantum eraser experiment gets even stranger when scaled up. Imagine a version where the choice to erase quantum information is made light-years away. The experiment suggests the distant choice would still retroactively determine what happens locally, but without transmitting any usable information faster than light. It's as if the universe maintains consistency through a cosmic conspiracy, ensuring that no matter how we try to exploit quantum mechanics, we can't send messages to the past or faster than light. Variable speed of light cosmology attempted to solve the horizon problem without inflation. If light traveled faster in the early universe, distant regions could have communicated and reached thermal equilibrium. But observations of the cosmic microwave background and distant quasars show no evidence for changing light speed. The fine structure constant, which would vary if light speed changed, appears constant to 1 part in a million over billions of years. The universe's speed limit seems truly immutable. The Unruh effect predicts that accelerating observers see blackbody radiation where stationary observers see vacuum. At the accelerations needed to approach light speed, this radiation becomes intense enough to incinerate anything. Some theorists speculate this creates a natural barrier. The closer you get to light speed, the hotter space becomes from your perspective, until further acceleration is impossible. The universe might enforce its speed limit through a wall of fire, visible only to those who approach it. Primordial black holes, if they exist, might offer clues about faster-than-light physics in the early universe. These black holes would have formed from extreme density fluctuations when exotic physics might have operated. Studying their properties could reveal whether the young universe had different rules, but searches for primordial black holes have found nothing conclusive. Even in its wild youth, the universe seems to have respected the speed of light. The simulation hypothesis adds a computational angle to the speed limit. If our universe is a simulation, the speed of light might represent the maximum rate at which the cosmic computer can process information. Trying to exceed it would be like trying to make a video game character move faster than the processor can calculate. Glitches at extreme speeds, like the increasing energy requirements to approach light speed, might be the simulation preventing overload. Of course, this is philosophy, not physics. Tachyon condensation in string theory shows how the universe might eliminate faster-than-light particles. Even if tachyons could exist, they would be unstable, quickly decaying into ordinary slower-than-light particles. The universe seems to have self-correcting mechanisms that eliminate anything threatening causality. It's like an immune system protecting the integrity of space-time from faster-than-light infections. The trans-Planckian problem questions what happens when quantum effects meet relativity at extreme scales. As we boost to higher speeds, quantum fluctuations get blue-shifted to shorter wavelengths. Eventually, they'd reach the Planck length, where our physics breaks down. This might create a fundamental barrier to approaching light speed, not just engineering difficulties, but a breakdown of the very concepts of space and motion. The universe might become undefined at speeds too close to light. Cosmic inflation itself presents a paradox. The universe expanded faster than light, solving several cosmological problems. But this superluminal expansion created regions forever beyond causal contact. If faster-than-light expansion was necessary to create our observable universe, why does the universe now forbid it? Perhaps the speed limit emerged after inflation, or operates differently for space itself versus objects within space. The early universe might have had freedoms that no longer exist. The quantum Cheshire cat effect allows particle properties to be separated from particles themselves, a grin without a cat, as it were. Scientists have separated neutrons from their magnetic moments in quantum experiments. Some theorize this property separation might enable faster-than-light effects by sending properties ahead of particles. But experiments show the properties still can't exceed light speed. Even disembodied quantum grins respect Einstein's ultimate speed limit. Modified theories of gravity like MOND attempt to explain cosmic observations without dark matter. Some versions predict variations in the effective speed of light under extreme conditions. If gravity works differently than Einstein predicted, perhaps the speed limit has loopholes we haven't discovered. But precision tests keep confirming general relativity. Every alternative theory either fails experimental tests or preserves the cosmic speed limit in a different form. The chronology protection conjecture remains unproven but compelling. Stephen Hawking proposed that the laws of physics always prevent time travel paradoxes, possibly through quantum effects that destroy any would-be time machine. The universe might allow microscopic violations of causality that average out, but prevent macroscopic faster-than-light travel that would create paradoxes. It's as if nature has a horror of paradoxes stronger than any physical force. The photoelectric effect that won Einstein his Nobel Prize shows light's particle nature, but it also demonstrates something profound about cosmic speed limits. Individual photons always travel at exactly light speed in vacuum, never faster, never slower. They can be slowed in materials or appear to move faster through anomalous dispersion, but in empty space, every photon maintains the exact same velocity. This universality suggests the speed limit isn't just a rule, but a fundamental property of existence itself. Let's explore what happens when we push matter to extreme speeds. The Large Hadron Collider accelerates protons to 99.99999% the speed of light. At these velocities, the proton's mass effectively increases by a factor of 7,000. The energy required for each tiny increment of additional speed grows exponentially. The final push from 99.9% to 99.99% requires far more energy than the entire journey from rest. The universe doesn't just set a speed limit, it makes approaching that limit increasingly expensive. Quantum teleportation has achieved remarkable feats, transmitting quantum states between particles separated by thousands of kilometers. Chinese scientists used the Meteor satellite to teleport photons from Earth to orbit. But despite the name, nothing actually travels faster than light. The quantum information can only be retrieved by comparing results through classical channels, limited to light speed. It's like having two locked boxes that always contain opposite items, mysterious but useless for faster-than-light communication without comparing notes. The cosmic web structure tells us something profound about the universe's speed limit. Galaxies are connected by vast filaments of dark matter, forming a web-like pattern across billions of light-years. This structure formed because gravity, limited to light speed, could only pull matter together gradually over cosmic time. If gravity acted instantaneously, the universe would look completely different. The very architecture of the cosmos is shaped by the finite speed of causality. Gamma-ray bursts, the universe's most powerful explosions, accelerate particles to speeds so close to light that time dilation becomes extreme. From the particles' perspective, their journey across the universe takes moments while billions of years pass in the outside universe. Yet even these cosmic accelerators, powered by collapsing stars or merging black holes, can't push particles past the ultimate barrier. Nature demonstrates both the possibility of reaching incredible speeds and the impossibility of exceeding the limit. The Pioneer anomaly puzzled scientists for decades. The Pioneer 10 and 11 spacecraft experienced tiny, unexpected accelerations as they left the solar system. Some speculated about new physics that might enable faster-than-light travel, but the mystery's solution was mundane. Thermal radiation from the spacecraft's power sources created a tiny thrust. This shows how desperately we search for loopholes in the cosmic speed limit and how nature consistently disappoints these hopes. Metamaterials have achieved the impossible on small scales: negative refraction, invisibility cloaking, and apparent faster-than-light pulse propagation. Scientists have created materials where the group velocity exceeds light speed, making wave packets appear to exit before entering, but information velocity remains stubbornly subluminal. These experiments demonstrate that while we can create illusions of faster-than-light motion, the universe distinguishes between appearance and reality, between wave velocities and actual signal transmission. The integrated Sachs-Wolf effect shows how cosmic expansion affects light travel. Photons crossing large cosmic voids gain energy as the void expands during their passage. This creates cold spots in the cosmic microwave background. The effect demonstrates how space's expansion influences light's journey without violating the speed limit. Even as space stretches beneath them, photons maintain their constant velocity, like runners on an expanding treadmill. String theory's extra dimensions might seem to offer shortcuts through higher dimensional space. If our three-dimensional universe is like a sheet of paper, perhaps we could fold it and punch through, traveling between distant points instantly. But calculations show that even in theories with extra dimensions, the speed of light remains the maximum velocity for information transfer. Higher dimensions don't provide loopholes, they just make the speed limit apply in more directions. The quantum Zeno effect demonstrates time's strange behavior in quantum mechanics. Frequent measurements can freeze a quantum system's evolution. At speeds approaching light, the universe's constant interaction might create similar freezing. Some theorists speculate this creates the speed barrier. Reality itself becomes undefined as you approach light speed, like a computer game glitching at its processing limits. The universe might protect causality by making faster-than-light travel literally meaningless. Observations of distant supernovae revealed the universe's accelerating expansion and dark energy. This discovery showed that most of the universe is already beyond our reach, receding faster than light due to space's expansion. Even if we could travel at light speed, we could only reach about 3% of currently observable galaxies. The rest are doomed to fade beyond the cosmic horizon. The universe hasn't just set a speed limit, it's using that limit to isolate regions from each other permanently. The double-slit experiment's delayed choice variant suggests quantum mechanics allows retrocausality, future measurements affecting past events. Some interpret this as faster-than-light influence traveling backward in time, but careful analysis shows no violation of causality. The universe permits quantum strangeness that seems to transcend time while still protecting the logical flow of cause and effect. It's like allowing plot twists that recontextualize earlier events without actually changing them. Hawking radiation demonstrates how even black holes respect the speed limit. As black holes evaporate through quantum effects, they release radiation at exactly light speed. Even at the event horizon where space-time curvature approaches infinity, nothing escapes faster than light. The universe's most extreme objects, where space and time break down, still obey this fundamental constraint. If black holes can't break the rules, what chance do we have? The equivalence principle, Einstein's happiest thought, reveals why gravity and acceleration are indistinguishable. This principle led to general relativity and explains why even gravity can't exceed light speed. When massive objects move, the changes in space-time curvature ripple outward at exactly light speed, like waves on a cosmic pond. The LIGO detection of gravitational waves from colliding black holes confirmed this precisely. Even the fabric of reality itself can't send signals faster than light. Let's consider the bizarre world of negative energy. The Casimir effect proves that empty space between conducting plates has less energy than regular vacuum, negative energy density relative to surroundings. This exotic energy is exactly what wormholes and warp drives need to function, but the effect is incredibly weak, and nobody knows how to amplify it to useful scales. It's like discovering you need a specific rare element to build faster-than-light ships, then learning you can only produce atoms of it at a time. The quantum eraser takes on cosmic proportions when we consider astronomical observations. Light from distant galaxies carries quantum information about its source. In principle, measurements we make now could retroactively determine quantum states of atoms billions of years ago. Yet this apparent backward-in-time influence can't carry usable information. The universe permits quantum correlations across billions of years while still preventing faster-than-light communication. It's cosmic censorship at its finest. Frame dragging around rotating black holes creates regions where space itself is dragged along, forcing everything to rotate with the black hole. In these ergospheres, even light must spiral around the black hole. Some theorists proposed extracting energy or achieving faster-than-light effects using this dragged spacetime. But calculations show that while you can steal energy from the black hole's rotation, you can't exceed light speed. Even in the most twisted spacetime the cosmic speed limit holds, the Hubble constant tells us how fast space expands, about 70 kilometers per second per megaparsec. This means galaxies separated by about 4,200 megaparsecs are receding from each other at light speed. Beyond this distance, galaxies recede faster than light, creating a cosmic event horizon. This isn't science fiction, it's the observed reality of our expanding universe. We live in a cosmos where faster-than-light separation is not only possible, but inevitable given enough distance. Quantum field theory in curved spacetime predicts particle creation in expanding universes. During inflation, the rapid expansion created particles from quantum fluctuations. Some theorists wonder if extreme spacetime curvature could enable faster-than-light effects through similar quantum processes. But calculations show particle creation respects causality even in the most extreme conditions. The universe might bend its rules during cosmic inflation, but it never breaks them. The Bootstrap paradox shows why faster-than-light travel threatens logical consistency. Imagine finding instructions for a faster-than-light drive in an ancient tomb, building it, then traveling back to place those instructions in the tomb. Where did the information originate? Such causal loops would make the universe logically inconsistent. Perhaps the speed of light is less a speed limit and more a logical necessity, the minimum required for a universe that makes sense. Cherenkov detectors use the blue glow of particles exceeding light speed in water to study neutrinos and cosmic rays. The ice cube detector at the South Pole uses a cubic kilometer of ice as a natural Cherenkov detector. These experiments show that exceeding light speed in a medium is not only possible but useful for science. Yet this offers no path to faster-than-light travel through vacuum. The universe allows us to break the speed limit where it doesn't matter but maintains it where it does. The cosmological constant problem highlights how little we understand about vacuum energy. Theory predicts vacuum energy density 120 orders of magnitude larger than observed. This spectacular failure suggests we're missing something fundamental about empty space. Perhaps this missing understanding holds keys to faster-than-light travel, or perhaps it explains why such travel is impossible. Either way, the vacuum of space holds secrets we haven't begun to uncover. Sonic black holes in Bose-Einstein condensates create acoustic horizons where sound cannot escape. These laboratory analogues of black holes exhibit Hawking radiation and other predicted effects. Some physicists hope studying these systems might reveal loopholes in horizons that could apply to real black holes or the light-speed barrier, but so far these experiments have only confirmed that horizons, whether for sound or light, are remarkably robust barriers that nature seems determined to maintain. The multiverse hypothesis suggests our universe is one of many, each with potentially different physical constants. In some universes, the speed of light might be different or not exist as a limit at all. But this offers no practical hope for faster-than-light travel. We're stuck in our universe with our speed limit. Even if other universes have different rules, we can't access them. It's like being in a prison and learning that other prisons have different rules. Interesting, but unhelpful. Closed time-like curves near rotating black holes theoretically permit time travel. The Kerr metric allows paths that loop through time, arriving before they departed. But these curves exist only in extreme gravitational fields that would destroy any traveler. Recent quantum calculations suggest that vacuum fluctuations would destroy any attempted time machine. Once again, general relativity seems to permit faster-than-light effects in principle, while quantum mechanics forbids them in practice. The information paradox extends beyond black holes to any attempt at faster-than-light travel. Information theory sets fundamental limits on how quickly information can be processed and transmitted. These limits seem deeply connected to the speed of light. Perhaps the universe's speed limit isn't about motion through space, but about information flow through reality. We can't travel faster than light because we can't process information faster than reality allows. The ADS-CFT correspondence, one of string theory's most profound discoveries, suggests our universe might be holographically encoded on its boundary. This duality implies that physics in our three-dimensional space corresponds to different physics on a two-dimensional surface. Some theorists speculate this could allow apparent faster-than-light effects in our 3D world that correspond to ordinary physics in the 2D description. But the correspondence preserves causality. No information travels faster than light in either description. Even holographic universes respect Einstein's speed limit. Dark matter's invisibility tells us something crucial about the universe's structure. This mysterious substance interacts through gravity but not electromagnetism. If dark matter particles could travel faster than light, they would emit Cherenkov radiation in vacuum, glowing visibly as they exceeded light speed. The fact that dark matter remains dark confirms that even exotic, barely interacting particles obey the cosmic speed limit. The universe enforces its rules uniformly, regardless of particle type. The quantum vacuum isn't empty, but seethes with virtual particles and field fluctuations. Some theories propose that manipulating these vacuum fluctuations could enable faster-than-light travel. The dynamic Casimir effect shows that moving mirrors can convert virtual photons into real ones. Perhaps rapidly accelerating structures could surf vacuum fluctuations to exceed light speed. But calculations show that vacuum effects respect causality. The quantum foam might be turbulent, but it still flows at or below light speed. Pulsar timing arrays search for gravitational waves by monitoring millisecond pulsars with extraordinary precision. These cosmic clocks would reveal any variations in the speed of gravity or light over cosmic distances. After decades of observation, they found no evidence that these fundamental speeds vary. The universe maintains its speed limit with clockwork precision across billions of light years and billions of years. If there were loopholes, pulsar timing would have revealed them. The quantum Hall effect demonstrates how topology can create robust physical phenomena. In certain materials, electrical resistance becomes quantized due to topological properties that persist despite impurities or imperfections. Some theorists wonder if space-time might have similar topological features that could enable faster-than-light shortcuts. But topological protection works both ways. It might make the cosmic speed limit even more unbreakable, not less. Neutrino oscillations prove these ghostly particles have mass and therefore can't reach light speed. For decades, physicists thought neutrinos were massless and traveled at exactly light speed. The discovery of neutrino mass through oscillation experiments showed that even particles that barely interact with matter must respect the universal speed limit. Every time we think we've found a particle that might break the rules, deeper investigation shows it doesn't. The opera experiment's false alarm illustrates how desperately physicists search for speed limit violations. In 2011, researchers announced neutrinos had arrived 60 nanoseconds early from CERN to Gran Sasso, suggesting faster-than-light travel. The physics world went into overdrive, proposing theories to explain it. But the culprit was a loose fiber optic cable causing timing errors. The episode showed both how seriously physicists take the speed limit and how carefully they verify any claimed violations. Cosmic voids offer natural laboratories for testing whether empty space permits faster-than-light travel. These vast regions contain almost no matter approaching the ideal vacuum. If the speed limit could be broken anywhere, it would be here. But observations of light-crossing voids show no acceleration or unusual effects. Even in the emptiest regions of space, spanning hundreds of millions of light-years, photons trudge along at their usual cosmic speed limit. The firewall paradox suggests that quantum mechanics might create barriers more fundamental than event horizons. If black hole horizons must have firewalls to preserve quantum information, perhaps the approach to light speed has a similar quantum firewall. As you accelerate toward light speed, quantum effects might create an impenetrable barrier of infinite energy. The universe might enforce its speed limit not through gentle resistance but through walls of quantum fire. Analog gravity experiments use sound waves in flowing fluids to simulate black holes and cosmological phenomena. These systems can exhibit sonic horizons and even analog Hawking radiation. Researchers hope these accessible experiments might reveal unexpected physics applicable to real gravitational systems. But so far they've only confirmed that horizons, whether for sound or light, behave exactly as theory predicts. Nature seems consistent in how it implements barriers to signal propagation. The many worlds interpretation suggests every quantum event branches the universe. If true, perhaps what seems like faster-than-light travel in one branch is just selection of a branch where you're already at your destination. But this offers no practical advantage. You can't choose which branch you're in or communicate between branches. Even in an infinite multiverse of possibilities, causality remains protected in each individual timeline. Loop quantum cosmology attempts to extend loop quantum gravity to the entire universe. In this framework, the Big Bang becomes a big bounce, with a previous universe contracting then expanding. Some speculate that physics might be different on either side of the bounce, perhaps allowing faster-than-light travel in certain epochs. But evidence suggests physical laws remain constant through cosmic time. The speed of light seems as permanent as existence itself. The measurement problem in quantum mechanics highlights our incomplete understanding of reality. We don't fully grasp how quantum possibilities become classical realities. Perhaps this gap hides the secret to faster-than-light travel. Or perhaps it explains why such travel is forbidden. Until we solve the measurement problem, we can't be certain we understand the universe's ultimate limits. But every experiment confirms that whatever the deep reality, it respects Einstein's speed limit. The quantum eraser delayed choice cosmology experiment pushes the boundaries of what we thought possible. Imagine making a measurement today that retroactively determines whether light from a distant galaxy billions of years ago behaved as a wave or particle. This has been demonstrated on smaller scales, suggesting our observations now can influence the quantum history of the universe. Yet even this mind-bending phenomenon can't be exploited for faster-than-light communication. The universe allows retroactive quantum determination while protecting causality, a delicate balance that suggests deep principles we don't yet understand. Let's examine what happens when we combine special and general relativity at extreme scales. In flat spacetime, the speed limit is absolute, but in curved spacetime near massive objects, the situation becomes more complex. Light follows curved paths that take longer than straight lines would. From one perspective, light slows down in gravitational fields. From another, it maintains constant speed through curved space. This ambiguity hints that the speed of light might be more subtle than a simple, universal constant. The Unruh-Hawking effect bridges quantum mechanics and relativity in profound ways. Accelerating observers see thermal radiation where stationary observers see vacuum. At the accelerations needed to approach light speed, this radiation becomes a blazing inferno. Some interpret this as the universe's enforcement mechanism. Try to break the speed limit and you'll be incinerated by radiation that exists only from your perspective. It's as if space-time itself resists violations of its fundamental rules. Quantum gravity proposes that space-time might have a discrete, graph-like structure at the Planck scale. In this model, space emerges from network connections between fundamental nodes. Perhaps faster-than-light travel could be achieved by rewiring these connections, creating shortcuts through the cosmic graph. But calculations suggest that even in discrete space-time, information flow is limited by causality constraints equivalent to the speed of light. The universe's speed limit might be more fundamental than space itself. The cosmic neutrino background, relic neutrinos from the Big Bang, fills space with particles moving at nearly light speed. These ancient neutrinos have been traveling for 13.8 billion years, yet they haven't exceeded the cosmic speed limit. If particles present since the universe's birth can't break the speed limit after billions of years of travel, it suggests the limit is truly absolute. Even the universe's oldest travelers respect Einstein's rules. Metamaterial analogues of cosmological phenomena offer tantalizing possibilities. Scientists have created materials where light behaves as if in curved space-time, exhibiting effects like event horizons and Hawking radiation. Some propose metamaterials that could create effective faster-than-light propagation by manipulating the local properties of space. But these materials only work for specific wavelengths and can't genuinely violate causality. They're illusions that reveal how desperate we are to find loopholes. The black hole bomb phenomenon shows how rotation and quantum effects combine in extreme ways. Superradiant scattering can extract energy from rotating black holes, potentially creating runaway effects. Some theorists wondered if this could enable faster-than-light phenomena by stealing energy and angular momentum from black holes, but detailed calculations show the process respects all known limits. Even when stealing energy from the universe's most extreme objects, we can't exceed light speed. Quantum discord, a measure of quantum correlations beyond entanglement, reveals subtler connections between quantum systems. These correlations persist even when entanglement vanishes, suggesting deeper layers of quantum reality. Perhaps these subtle correlations could enable faster-than-light effects we haven't recognized. But experiments consistently show that discord, like entanglement, can't transmit information faster than light. Each new quantum phenomenon we discover respects the same fundamental limit. The photon sphere around black holes creates a region where light orbits in unstable circles. Photons can circle black holes multiple times before escaping or falling in. This creates optical illusions where we see multiple images of the same object at different times. Some wondered if these light-trapping regions could be exploited for faster-than-light effects. But the photon sphere demonstrates the opposite. Even light can be trapped and delayed by gravity, never exceeding its fundamental speed. Vacuum birefringence predicted by quantum electrodynamics and recently observed near neutron stars shows that extreme magnetic fields can affect light propagation. In these conditions, vacuum acts like a crystal, splitting light based on polarization. This proves that vacuum isn't simply empty but has structure that emerges under extreme conditions. Yet even these exotic vacuum properties don't permit faster-than-light propagation. The universe reveals new phenomena while maintaining its speed limit. The holometer experiment at Fermilab searched for pixelation of space-time at the smallest scales. Using laser interferometry, it looked for fundamental graininess that might affect light propagation. Finding such pixels could revolutionize physics and perhaps reveal faster-than-light shortcuts between pixels. But the experiment found smooth space-time down to incredible precision. If space is pixelated, the pixels are far smaller than we can detect, offering no practical shortcuts. Tachyon field theory in cosmology proposes that the early universe might have contained faster-than-light fields that drove inflation. These primordial tachyons would have decayed quickly, leaving our universe with its current speed limit. It's like the universe had a wild youth with different rules before settling into middle age with strict cosmic speed limits. This could explain why inflation exceeded light speed while current physics forbids it. The quantum Cheshire cat's grin might travel separately from its body, but experiments show both property and particle respect light speed. Scientists have separated quantum properties from their particles in interferometry experiments. If properties could travel faster than particles, it might enable faster-than-light information transfer. But nature maintains synchronization. Properties and particles remain causally connected despite separation. Even quantum grins can't exceed the cosmic speed limit. The story of faster-than-light physics is really a story about human ambition meeting cosmic law. We've discovered that space itself can expand faster than light, carrying galaxies beyond our reach. We've found quantum correlations that span the universe instantaneously. We've detected particles that tunnel through barriers as if space doesn't exist. Yet none of these phenomena allow us to send a message, transport an object, or violate causality at speeds exceeding light. The universe seems to say, you can bend the rules, but you cannot break them. Consider what we've learned from gravitational waves. When LIGO detected the collision of black holes 1.3 billion light-years away, those waves had been traveling at exactly light speed since before multicellular life existed on Earth. Not faster, not slower, exactly the speed of light. Even cataclysmic events that shake the fabric of space-time itself can't push information beyond this limit. If colliding black holes can't break the speed limit, what hope do human technologies have? the quantum eraser, entanglement, and tunneling all hint at a deeper truth. The universe processes information in ways that transcend our classical understanding while still protecting causality. It's as if reality runs on a cosmic operating system that allows quantum shortcuts for correlation but blocks any attempt to use them for communication. We can have spooky action at a distance as long as we can't send messages through it. The universe permits mystery while preventing paradox. Dark energy's acceleration of cosmic expansion reveals the ultimate irony. The universe is not only enforcing a speed limit, but using it to isolate regions from each other permanently. Galaxies we see today will eventually disappear beyond the cosmic horizon, receding faster than light due to expanding space. In the far future, civilizations will emerge in island universes unable to see beyond their local group. The cosmic speed limit doesn't just constrain us, it's slowly drawing curtains across the universe. But here's what fills me with wonder rather than despair. The very fact that we've discovered these limits represents humanity's greatest intellectual achievement. We're arrangements of atoms that have figured out the fundamental rules governing atoms. We've measured the unmeasurable, understood the seemingly paradoxical, and mapped the boundaries of possible. The speed of light might limit our bodies, but it hasn't limited our minds. The search for faster-than-light travel has taught us profound lessons about the universe. We've learned that information and energy are fundamentally connected. We've discovered that space and time are aspects of a unified space-time. We've found that quantum mechanics and relativity, seemingly incompatible, both respect the same cosmic speed limit. Each failed attempt to exceed light speed has deepened our understanding of why the universe works the way it does. Think about the experiments we've discussed, from the Large Hadron Collider accelerating particles to near light speed, to LIGO detecting space-time ripples from ancient collisions. Each confirmation of the speed limit required incredible ingenuity to test. We've built detectors that can measure distances smaller than a proton, telescopes that can see to the edge of the observable universe, and theories that explain phenomena across 40 orders of magnitude. The speed limit hasn't stopped us from exploring, it's challenged us to be more creative. The quantum technologies emerging from our understanding of entanglement, quantum computers, quantum cryptography, quantum sensors, show that respecting the speed limit doesn't mean technological stagnation. We're learning to exploit the universe's quantum rules to process information in ways that classical physics never allowed. We might not be able to send signals faster than light, but we can compute solutions to problems that would take classical computers longer than the age of the universe. Perhaps the most profound revelation is that the speed of light connects everything in the universe. Every photon that reaches your eye from a distant star creates a real, physical connection across space and time. You're not just observing the universe, you're interacting with it through electromagnetic fields that respect the cosmic speed limit. When you see the Andromeda Galaxy, photons that left 2 million years ago are completing their journey by triggering chemical reactions in your retina. The speed limit doesn't separate us from the cosmos, it's the very thing that connects us to it. The future of physics might reveal new understanding about the speed of light. Perhaps it's emergent from something deeper. Perhaps quantum gravity will show us why this particular speed is special. Perhaps we'll discover that what we call the speed of light is just one aspect of a more fundamental principle. But every indication suggests that causality, the logical flow from cause to effect, will remain protected. The universe might surprise us with new physics, but it won't let us send messages to our past. As we look toward the stars, knowing that most of them are forever beyond our physical reach, we face a choice. We can despair at our cosmic imprisonment, or we can marvel at what we can achieve within our constraints. We've sent robots to every planet, decoded the cosmic microwave background, detected gravitational waves from colliding black holes, and discovered thousands of exoplanets. We've done all this while barely leaving our cosmic neighborhood. Imagine what we might achieve in the coming centuries, working within the universe's rules rather than raging against them. The speed of light teaches us humility and inspires ingenuity. It shows us that the universe has absolute laws that no amount of human desire can overcome. But it also challenges us to find clever solutions, to think in ways that respect these limits while achieving seemingly impossible goals. Every spacecraft that uses gravitational slingshots, every telescope that uses gravitational lensing, every quantum computer that exploits entanglement, these are triumphs of human creativity working within cosmic law. So can anything travel faster than light? The answer, based on everything we know, is no, not in any way that violates causality or allows faster-than-light communication. Space can expand faster than light, quantum correlations can span the universe instantly, and theoretical constructs like tachyons can exist in equations. But nothing that carries information, nothing that could create a paradox, nothing that would break the logical structure of cause and effect can exceed this ultimate speed. This isn't a failing of physics or a limitation we'll eventually overcome. It's a fundamental feature of a universe that makes sense, where effects follow causes, where time flows forward, and where the laws of physics are consistent. The speed of light isn't our enemy, it's the guardian of cosmic order, the protector of causality, and the foundation of a comprehensible universe. Thank you for joining me on this exploration of physics' ultimate speed limit. If this journey through the boundaries of possible has expanded your understanding of our incredible yet limited universe, please share this video with someone who dreams of the stars. Subscribe to continue exploring the deepest mysteries of space and time, and remember, we might be forever bound by the speed of light, but our curiosity and wonder know no limits. What other cosmic mysteries should we explore next? Leave your suggestions in the comments below. Until next time, keep looking up, keep asking why, and never forget that understanding our limits is the first step to transcending them in ways we haven't yet imagined. If you are still watching, make sure to subscribe to the channel and give a thumbs up. And if you want to keep exploring the mysteries of the universe, I am sure you will love this other video at the left side of the screen. What if we could travel at light speed today? Discover what would actually happen if you could accelerate to the speed of light, from time dilation and length contraction to the Doppler effect, relativistic aberration, and the deadly hazards of interstellar travel. See you there.